All right, guys, today we're going to talk about Newton's laws of motion and how they affect forces. Let's take a look. First of all, let's talk about what it means to be a law in the scientific sense. A law, when we're talking science, is a rule that has been developed to explain repeated observations. And so they are defining what is happening. This is different from a theory, which describes why something happens. And so this guy Newton came up with some laws to describe how objects move. And he saw that they do this every time, but the laws don't exactly explain why the objects move. That's something we'll look at later. So there are three laws that Newton came up with. And the first one is also called the law of inertia. What it says specifically is that an object that is in motion will stay in motion, and likewise an object that is at rest will stay at rest until they are acted on by an unbalanced force, which we talked about last class. This introduces us to the property of inertia, which is how likely something is to not change what it is doing. This is based on mass. The more mass something has, the more inertia it will have, and that means that you will require more force to change its motion. So heavier things need more force in order to move or stop. So what do changes in motion look like? This is something we've talked about before. We're thinking acceleration here, so go ahead and write down the three things that you know change motion, and then I'll let you know what they are. Hopefully you got them. They are that you can increase speed or start to move, you can slow down or stop, or you can change directions. These are the three things that change our motion. So let's take a look at these pictures, and I want you to circle the object in each pair that has the most inertia and explain why, based on what we just talked about. All right, and so I will go ahead and circle these ones to show you, but over here we have an elephant and a mouse. The elephant would have more inertia. We have a mountain and a molehill. The mountain is going to have more inertia. And we have a car and a motorcycle. Here the car will have more inertia. And the reason why is that they all have more mass. So again, if you have more mass, it's going to be harder to have a change in motion, and therefore you will have more inertia. And so we can use the first law to describe what is going to happen to an object's motion as we're watching it. So look through these scenarios and try and describe what you think will happen based on what we know now about Newton's first law of motion. The first scenario is a car is left on a flat driveway overnight. Where will that car be in the morning? Pause here and I'll let you know the answer in a few seconds. And the answer is, it's still going to be there because no force has been applied to it. If the car has moved, then somebody probably applied an illegal force to it. Your car has been stolen, unfortunately. Let's look at the next scenario. The next scenario is we have some kids gliding on ice, and they are just out there without skates, so kind of gliding around on their shoes, and they are pushing off of each other in order to move around. What is going to happen to their motion? Take a few seconds, figure out an answer, and I'll be back. The answer is that they will continue moving in the same direction at the same speed unless there is another force applied to them to make them accelerate or decelerate. So what we've seen with Newton's first law is that they will keep moving in the same direction unless something happens, like they get to the end of the ice or one of their friends comes and bumps into them and pushes them in another direction. And in our third scenario, we have a ball rolling across a grassy area. The question here is, why does it stop after 5 meters? Think about that. I'll be back with the answer in just a bit. Our answer here is friction. So we know that there's this force out there called friction, and it is slowing down the ball because it works in an it works as an unbalanced force in the opposite direction to the ball's motion. So the ball is moving forward, friction works against it backwards, causing the ball to slow down. And friction will happen anywhere where two objects are moving on top of each other. Okay, so let's look at the second law. Newton's second law describes a relationship between force, mass, and acceleration. And specifically, it's saying that the acceleration of an object is proportional to the force and the mass of the object. And this is the reason why we have a constant acceleration of 9.8 meters per second squared on Earth. Gravity is a force acting on objects, and it's going to change just depending on their mass. From the second law, we get an equation that looks like this. Force is equal to mass times acceleration. And so we can use that formula to calculate different things. Let's work through these problems. The first one is asking us how much force would it take for a man to push a child who weighs 80 kilograms on a swing with an acceleration of 5 meters per second squared. So let's plug that into our equation. We know that force is equal to mass times acceleration. So our mass here is 80 kilograms. And our acceleration is 5 meters per second squared. And if you multiply that out, you're going to see that it is equal to 400. And remember, our unit for force is newtons. In order to get a correct answer, make sure that you are using kilograms for mass, meters per second squared for acceleration, and newtons for your force when you're plugging into this equation. Let's look at the next question. This one is asking us how fast would a rock travel if it has a mass of 5 kilograms and thrown with a force of 10 newtons. So our key word here is fast. That means this time we're looking for acceleration. And so we'll have to rearrange the formula a little bit. We can still use the same formula, force equals mass times acceleration. But now we want to solve for acceleration. So we're just going to divide both sides by mass. And we'll see that acceleration is equal to force divided by mass. Now remember, if you get confused with rearranging equations, since this is a 3-variable equation, you can use your triangle again. In the triangle, we're going to write the formula. We have, in this case, force being equal to mass times acceleration. And if I cover up, in this case, acceleration, I'm left with force divided by mass. If we plug in our numbers for this question, we have a force of 10 newtons and a mass of 5 kilograms, which means that our acceleration is going to be 2 meters per second squared. And this third question asks us how heavy is an object falling on Earth if it has an acceleration of 9.8 meters per second squared and the force of gravity is 72 newtons. In this case, our keyword is heavy. Heavy means we're looking for mass. So we'll rearrange the formula one more time. Divide both sides by acceleration to single out mass. And we'll see that force is divided by acceleration to find our mass. Quick look at the triangle again. If you cover up if you cover up mass, you'll see the same thing, force divided by acceleration. And so we'll plug in our numbers here, and mass is going to be equal to a force of 72 newtons divided by an acceleration of 9.8 meters per second squared. And our answer is we have a mass of 7.3 kilograms. And I just rounded to the 10th place there. Newton's third and final law of motion states that every action force has an equal and opposite reaction. So if you apply a force to something, it will apply a force back. Take a look at this swimmer, for example. The swimmer is not pushing on himself in order to move. He is pushing on the water. And so the water is pushing back on the swimmer. So as he pushes his arms through the water, he's pushing down on the water, and the water pushes back on him. Otherwise, he wouldn't be able to move. He would just be pushing on something, but he would just go straight through it. So let's take a look at a few more examples of this law. So remember, there's always two forces that are acting in different directions. And so in these pictures, we're going to draw the action force that is taking place and the reaction that happens to it. In this first picture, we have two skaters pushing on each other, and we'll look at this guy on the right and what happens with him. He is pushing against the lady, so that's his action. And what's going to happen is he is going to move backwards. That will be the reaction because the lady is pushing against him, and so his motion will be to move backwards on the ice. In the second situation, we have a guy about to jump off a boat, and so the action here is that he will jump forward. When he does that, the boat's pushing against him and he's pushing against the boat, so the boat will move backwards, and that will be the reaction. Finally, we have this space shuttle blasting off. The action here is that the engines ignite and provide thrust downwards. As the rockets ignite, they push the rest of the spacecraft up. And so the action here is that we have the rocket launch, and the reaction is that the space shuttle blasts up into space. So those are Newton's 3 laws, and today you are doing other activities to see these in action. And a little later on in the year, we will be launching our own rockets to see these in a different way there as well. Let me know if you have any questions. Make sure you filled out everything in your notes, and have a good day, guys.